Hello, I welcome you all in this presentation related with the subject materials processing fundamentals and practical. In this particular talk, I will be highlighting the importance of the metal structure and its effect on the plasticity or the way by which ease of the plastic deformation is affected due to the variation in microstructure of the material. So, this the talk primarily will cover the metal strengthening mechanisms which are affecting the ease of deformation. So, metals are strengthened by various mechanisms to increase the hardness and strength, which in turn affects the ease of deformation. Then various deformation mechanisms like slip and twinning, about these also I will be talking, and how these two are different from each other, and then microstructural aspects that will be affecting the plasticity, about that we will talk in greater length, and then we will try to see how the temperature and structure will be affecting the plasticity. Like when the temperature is increased, there will be recovery, recrystallization, and the drop in yield strength, which in turn affect the plasticity. So, if we see that whenever at a room temperature, whenever a metal is subjected to the plastic deformation, you see, depending upon the kind of the metal, work hardening characteristics, the solid state phase transformation, microstructural changes which will be occurring, the metals experience variety of changes in terms of the mechanical properties. So, metals mechanical properties are affected, okay, and this effect comes from the work hardening, okay, this is one, and sometimes the deformation induced phase transformations also occur, okay. So, this is the another reason, deformation induced phase transformation. Additionally, the grain morphology is also modified due to the plastic deformation. So, the morphology of the grains, so that is also affected. So, we get a change in the phases, we get the change in the size and shape, the geometry of the grains, and even the work hardening effect in terms of the increased dislocation density is also observed. So, these factors in combination affect the mechanical properties significantly, and that is what we can see. Increasing plastic deformation increases the yield strength. This can be attributed to the multiple factors, including work hardening or the deformation induced phase transformation if it is occurring depending upon the kind of metal, and then the grain refinement, or the, you can say, the change in the grain morphology due to the plastic deformation. Okay, severe plastic deformation can cause the significant grain refinement. Okay, so this in turn increases the yield strength, and the similar trend is also observed for the hardness variation. So, hardness and yield strength both move together, and increase in strength and hardness is observed. But this happens at the cost of the ductility. So, the ductility comes down and the impact resistance also decreases. And there is an interesting change which occurs, that is the increase in the ductile to brittle transition temperature. This temperature indicates the temperature or a temperature range at which the sharp drop in the toughness will be taking place with the reduction in temperature. That we can understand from this simple diagram, where if we see, we have the toughness in the y axis and the temperature in the x axis. Say this temperature is 0 degree centigrade, then 10, 20, 30, 40, okay, positive side 30 and 40 degree centigrade. And on the left side, if you go minus 10, minus 20, minus 30. So, what happens to the toughness of the metal when it is exposed to the different temperatures? So, the metals like the mild steel and lot of alloy steels, what they do, how they behave is, there is a drop in their toughness like this. So, this drop occurs over a range of temperature. This is not one particular temperature. So, this temperature can be very sharp, or this temperature can fall gradually. this temperature range can be very wide or it can be very narrow range of temperature over which such kind of the sharp drop in temperature takes place. So, if the range is very wide, then what we do, we try to find the median value. Okay, and this drop can also be of the another kind if we try to see. Okay, and this drop can be like this also, where the drop is very sharp. Okay, so here it is little easier to identify the temperature at which this kind of the drop is, this temperature range is very narrow, and this temperature narrow temperature range over which such kind of the drop in toughness takes place with the reduction in temperature, that is known as dVTT. So, when the metal is subjected to the plastic deformation at a room temperature, many metals show increase in the value of this temperature. So, this temperature shifts on the higher side. So, means the metal which is ductile at a higher temperature starts showing the brittle behavior even at, like say, the room temperature condition. So, that is harmful because the metal will be losing its resistance to the impact or will be losing the toughness. So, this is the undesirable kind of the behavior which is observed. So, when a metal is subjected to the plastic deformation, these are the kind of changes which are experienced by the metal. So, the two properties, especially the yield strength and the percentage elongation, ductility in terms of the percentage elongation. So, ductility is compromised, ductility is reduced, and yield strength is increased. So, if we see from ease of deformation point of view, then this kind of the change is undesirable, because what we want, that for easy plastic deformation, if the material is having the lower yield strength and higher ductility in terms of say percentage elongation, then this will be resulting in easy plastic deformation of the metal to get the desired size and shape during the manufacturing by the deformation based material processing techniques. So, this is about the effect of the plastic deformation, change in mechanical properties, and the way by which it will be affecting the material processing by the deformation based approach. This is the another aspect where we will try to see what are the various metal related aspects affecting the plastic deformation or ease of plastic deformation. So, metal strengthening mechanisms, this is very important because it affects the way by which metal will respond to the heat, to the deformation when the deformation based material processing approach is applied. So, the metal can be strengthened by various mechanisms, can be solid solution strengthening, grain refinement, work hardening, precipitation hardening, dispersion hardening, transformation hardening. So, the each mechanism responds differently to the heat and to the deformation. So, we need to see like how a particular metal has been strengthened, and accordingly it will respond to the deformation or to the heat during the material processing by, like say, the deformation at room temperature or when the deformation is taking place at a higher temperature. Crystal structure is the another important aspect because it affects the ease of deformation significantly. Why? Because the different metals show the different types of the crystal structure due to the variation in arrangement of the atoms. So, the most common crystal structure is like the body centered, body cubic centered, BCC, FCC, and HCP. Okay. So, these are the most common crystal structures observed in common commercial metals and alloys. And depending upon the crystal structure, we find the different slip systems, and which in turn affect the ease with which the slip or the deformation that will be taking place in a metal, and that in turn affect the ease of the deformation or the plasticity of the material. Now, the microstructure, as far as the microstructure is concerned, we will try to look into the two aspects. One is the grain structure and another is phase structure. So, when we see the phase structure or the grain structure of the metal, these are the two aspects in a scope. So, we have to see like when the plastic deformation is taking place either at room temperature or at high temperature, how the phases are getting affected, say how the type of phase is getting affected, how the relative amount or the percentage or the relative amount of the each phase is getting affected, and how the distribution of the phases is getting affected, because all these will be determining the plasticity or ease of the deformation significantly. So, it is important to consider that. Likewise, when we talk of the grain structure, when we try to talk about the grain structure and its effect on the deformation, so there is a size of grain, average size of grain. This is one. Then the shape of grain, okay, and the next one is the distribution, where what kind of the what type of the grain, what size and shape of the grains are present. So, larger the grain, lower will be the yield strength, easier will be the deformation, like that. So, the grain structure has its own effect on the ease of deformation or the plasticity, and therefore, it is important to consider this. Okay. Another important aspect is the stacking fault energy associated with the particular metal. Each metal show a unique kind of the stacking fault energy, commonly known as SFE. So, metals with the high stacking fault energy, they show low work hardening tendency. Okay, they show low work hardening tendency means, if the metal like aluminum or magnesium having the higher stacking fault energy, when we deform them plastically, there is no significant work hardening, there is no significant increase in strength and the hardness. So, this makes the job of plastic deformation easier and to get the metal in a particular shape through the forming based processes. Okay. And when the metal is having the low stacking fault energy, okay, then it shows the great work hardening tendency. Increase the, you see, great work hardening tendency means increase as the deformation takes place, metal hardens rapidly. This requires greater amount of the energy, efforts, stresses to continue with the plastic deformation when a particular shape is being given during the material processing by forming. So, stacking fault energy of the metal determines how it will work harden during the deformation, especially under the room temperature conditions. Okay. And then deformation mechanism by the slip and twinning. So, these are the two deformation mechanisms based on the dislocation movement, and the slip is one and the twinning is another. So, these two mechanisms will be active under the different the strain rate conditions and the temperature conditions. Okay. So, depending upon the temperature and the rate of deformation or strain rate conditions, the two will be active during the deformation. Okay. Now, whenever in real practical applications, whenever a metal is deformed, both slip and tuning contribute towards the deformation. Only single mechanism does not contribute always only to cause the plastic deformation, but both will be active. So, there are many metal strengthening mechanisms which are used to design and develop the metals. So, it can be like the work hardening, precipitation hardening, transformation hardening, grain refinement, dispersion hardening and solid solution strengthening. Okay. So, if we see these first four mechanisms like work hardening, grain refinement, precipitation hardening and transformation hardening, these four mechanisms responds very rapidly to the heat. Okay. While the two mechanisms like dispersion hardening and the solid solution strengthening, response of these two mechanisms is limited to the heat applied. Okay. So, if we see when the metal is subjected to the deformation, how these mechanisms respond, or when metal is subjected to the heat, how these mechanisms respond, that in turn will be affecting the strength and hardness. So, say work hardening mechanism is simply based on the developing increased number of dislocations. Okay. So, when a metal designed based on the work hardening mechanisms, when it is subjected to the plastic deformation, number of dislocations increase. So, the increased density of the dislocations further increases the yield strength and hardness. Okay. This makes the deformation difficult and the plasticity is compromised. Okay. On the other hand, the precipitation hardening is based on the principle of developing the fine distributed hard precipitates in matrix of relatively soft metal. So, this is the soft metal and fine precipitates are distributed. So, what happens when the heat is applied, these precipitates tend to get dissolved. Okay. But when the metal is likewise, when metal is subjected to the severe plastic deformation, again these get fragmented and get dissolved. Okay. So, this will be leading to the softening, drop in yield strength, drop in an increased ease of the deformation due to the reduction in the yield strength. Now, if we talk of the grain refinement, the grain refinement effect of the grain refinement on the properties is relatively less, but most of the metals, like say if it is of the 50 micrometer grain size and if it is refined to the 20, there will be increase in strength and the hardness, and if it is further refined to the 5 micron size, then it will further increase the strength and hardness. But at the same time, if it is leading to the formation of the soft phases, okay, like say earlier you had reasonably hard phases but of the large size, okay, but if the refinement coupled with the formation of soft phases will not lead to the any significant increase in yield strength and hardness. So, if the phase remains intact, then the refinement causes the increase in yield strength and hardness. But if the phase gets modified, either it gets hardened or softened, then the relative effect of the grain size as compared to the phases will be limited. So, it is important that if the type of phase remains same, then the refinement is helpful, but if the phase is compromised, if the type of phase is becoming soft due to the processing, then despite of the refinement we do not find much increase in strength and the hardness. So, the relative effect of the grain refinement is somewhat limited as compared to the phase or phase transformation which is happening, which can happen during the deformation. So, that is what we can say the transformation hardening. Initially you may have soft phases offering very good deformation and ease of deformation and plasticity, but in course of the deformation or thermal treatment or high temperature deformation, if it is leading to the formation of the hard phases, then this will make the job of deformation difficult, this will reduce the plasticity, this will decrease the ease of deformation significantly. Okay. So, what we try to do is at room temperature, if the plastic deformation is causing the formation of the soft to hard phases, then this will certainly be compromising with the ease of deformation. But if at high temperature such kind of the deformation is carried out, it may not lead to the formation of the hard phases from the soft phases due to the deformation. Okay. So, there is another important thing, like the temperature at which deformation is carried out is extremely important, because at high temperature work hardening effect is very limited. It is there is a possibility of the dissolution and the loss of the precipitate. So, the harden means there will be decrease in yield strength due to the recovery, recrystallization and the loss of the precipitates, grain coarsening at a high temperature, coarsening of grains, and then there is a possibility of the formation of the soft phases. So, these four mechanisms will be compromised at a high temperature, which means all these will be contributing to reduction in the yield strength and increase in the ductility, which will make the job of a deformation easier. Okay. Effect of these two dispersion hardening mechanisms, which is particularly used for developing the composites, and solid solution strengthening, this is used particularly in most of the alloys. Okay. Effect of the deformation will be limited on the yield strength and the ductility of the metal, which has been strengthened by the dispersion hardening and solid solution strengthening only. Okay. So, now we will try to see the further other aspects. So, all these things I have already explained. So, now we will see the common metals and their crystal structure. So, now we will try to see how the crystal structure will be affecting the ease of deformation. We know that there are variety of the metals with the three most common types of the crystal structures, like body centered crystal structure BCC, face centered crystal structure FCC, and hexagonal packed crystal structure HCP. And this depends on the kind of arrangement that is there in a unit cell of a particular metal. This arrangement of the atom, which we see in terms of the crystal structure, affects the atomic packing factor, effective number of atoms associated with a particular unit cell, and their coordination number. And these factors in turn affect the slip systems, number of slip systems, which will be determining the ease of deformation of the metals. Okay. So, the common crystal structures are like the BCC structure. Crystal structure is found in alpha iron, that is ferrite, tungsten, cobalt, chromium, vanadium, etc. Then FCC is found in the aluminum, silver, gold, manganese, nickel, gamma, iron, copper, and HCP is found in the Mg and zinc. Okay. So, why it is important? Because crystal structure affects the number of slip systems associated with the particular metal. Lesser the number of slip systems, more is the difficult to cause the deformation, means it will require greater stress level to cause the plastic deformation. Okay. So, crystal structure determines the physical property, particularly the density, solid state solubility to the alloying elements, and the ease of deformation as per the mechanical property variation in terms of yield strength and ductility. Okay. So, the number of slip systems that are present in a given metal of a unit cell affect the ease of deformation. A large number of slip systems reduces the resistance to the plastic deformation. So, if a metal is having the greater number of slip systems, it will require lesser stresses to trigger the deformation, okay, by facilitating the movement of dislocations. Because deformation mechanisms become active at a much lower level of stress in a metal having more number of slip systems, like in copper and magnesium, in FCC metals, than those having the lesser number of slip systems, like in iron and tungsten. So, if FCC metals like aluminum and copper having the more number of the slip systems than that of the iron or tungsten, that will make the slip easier, and the slip will start at the lower level of stresses, which indirectly will reduce the resistance to deformation or will make the deformation easier. Okay. So, slip systems, as per the crystal structure, if we see, the yield strength of metal determines the resistance to the plastic deformation, which occurs. So, the plastic deformation usually occurs through slip or twinning or combination of these. These atomic scale mechanisms facilitate the plastic deformation by sliding of the atom of one layer over the another under the influence of the external stresses. So, one layer of atom will be sliding over the another layer of atom to facilitate the slip, facilitate the deformation by the slip or twinning mechanisms under the influence of external stresses. Okay. Sliding of atoms in a metal takes place in a certain crystallographic planes. These crystallographic planes, known to facilitate the slip or twinning, possess the maximum, the slip planes having the maximum atomic density. Okay. So, the planes having the maximum atomic density makes the slip or the deformation easier. So, these crystallographic planes having the maximum atomic density facilitate the slip to cause the deformation. These are called slip planes. Sliding of the atoms or the slip on a slip plane as per the external stresses and the metal system takes place in many directions. So, a combination of the slip plane and a slip direction, these two determines that how many slip systems will be there. Like if there are 3 slip planes and 4 directions, then it will be resulting in the 12 number of the slip systems. So, the most closed packed direction in a crystal structure is called the slip direction. combination formed by the various slip planes and various directions in a crystal structure facilitating the slip is called slip system. So, slips is, for example, FCC metal like aluminum having 4 slip planes and 3 slip directions, then it will have the 12 slip systems. So, the metals showing the more slip systems, they will be showing the easier deformation, or the deformation of the metal will be easy in those cases. So, under the influence of external stresses, metal having the higher number of the slip systems experiences the slip, leading to the deformation at the lower shear stress. So, the stress required to cause the plastic deformation, that will be reduced if metal is having the higher number of the slip systems. Therefore, plastic deformation of the metals having the FCC crystal structures takes place in easy manner as compared to the metals having the BCC crystal structure or HCP crystal structure, primarily due to the difference in number of slip systems. Okay. This is how we can understand why the metals with the different crystal structures show the different behavior in terms of the ease of plastic deformation. Further, the distortion in regular crystal structure of the metal affects the mechanical properties. For example, deformation of the BCC, body centered cubic metal, to the body centered tetragonal crystal structure BCT, okay, crystal structure due to the supersaturation of carbon in alpha iron, that is BCC, leads to the martensitic transformation in form of the BCT. So, alpha iron transformation during the heat treatment, like the hardening heat treatment, this will be causing the, like, BCC gets transformed into the martensite having the BCT. So, this is attributed to the distortion in lattice structure from the BCC to the BCT. Okay. This kind of the BCC to BCT transformation causes significant increase in the hardness of the iron, and increased degree of distortion in lattice of the crystal structure due to the supersaturation is attributed to the increase in hardness of the metal. So, there are various possibilities. The one is the number of slip systems that a metal has, and if the distortion in the lattice is also taking place due to the any reason, then that will also be increasing the yield strength and the hardness. Stacking fault energy is about the arrangement of the atoms which is defective. So, the stacking fault is the another crystalline surface defects affecting the response of the metal to the plastic deformation. So, if we see this diagram here, we can see there is an arrangement of a particular order in arrangement of the atoms, but here in this particular zone this arrangement is disturbed. So, this irregular arrangement of the atom is termed as the stacking fault, of the fault in stacking of the atoms. Okay. So, the energy associated with the stacking fault, usually termed as a stacking fault energy, one of the common ways to estimate or anticipate the response of the metal to the deformation. So, the low stacking fault energy metals like high magnesium steels, austenitic stainless steel, cobalt alloys, they show the high strain hardening tendency. So, they strain harden or work harden rapidly, increase the stress required to cause the further plastic deformation as compared to the high stacking fault energy metals like aluminum and magnesium. So, if we compare what happens to the stress requirement with the increasing strain, then we will see the increasing deformation leading to the increased dislocation density, that will be leading to the increase of yield strength. So, increase in yield strength is much higher for low stacking fault energy metals as compared to that for the high stacking fault energy metals. Okay. Grain size is the another factor that affects the yield strength and the ductility of the metals. Okay. Usually the grain size directly affects the yield strength of the metal, and what that is expressed using this one of the popularly known Hall patch relationship. So, sigma y is the yield strength and sigma I is the yield strength when the grain size is infinite, k is the coefficient, and divided by 1 by root d. D is the diameter of the grain. So, what it suggests that sigma y is inversely proportional to the square root of the d. Reducing the grains, so if we see, if the grain size is reduced, yield strength is increased, okay, and increasing the grain size will adversely affect the yield strength. So, this is particularly true when the grain size is up to a certain limit. That is what we can see, inverse of the grain size. This reduction in grain size increases the yield strength up to a certain limit, but below certain, when the grains becomes much finer, then the mechanism becomes different and the grain boundary sliding becomes active, and then the reversal of the Hall patch relationship is observed, and this may be like 30 or 40 nanometer. Otherwise, reduction in grain size like 50 to 1 micrometer or 800 nanometers. So, that in that case it will be causing the increase in yield strength, and because when the grain size is relatively large, the dislocation slip deformation occurs by the dislocation slip. When the grain size becomes extremely fine, then the deformation occurs through the grain boundary sliding. So, there is another diagram that shows the relationship between the grain size and the various metal characteristics. So, the reduction in grain size in general increases the yield strength, increases the resistance to the deformation, improves the ductility. So, these things, so if we see the reduction in grain size will increase the yield strength, which will require greater stresses to cause the plastic deformation, but at the same time it will facilitate the ductility, facilitate the deformation by improving the ductility. Now, the deformation by slip, so that there are two atomic level mechanisms through which the deformation occurs. The slip is one. So, the movement of one layer of atom over the another layer of atom needs the shear stresses above certain level to cause the slip. So, says this is an arrangement of atom, the stress is applied, shear stresses are applied, and when these stresses cross certain limit, one layer of the atom starts sliding over the another layer of atom. Slip takes place through the multiple atomic interatomic distances. Slip takes place through the multiple interatomic distance. So, interatomic distance is say A, then it will be N. So, it will be in multiple of the interatomic distances, not the fraction of the interatomic distances. Therefore, arrangement of the atom in deformed and undeformed regions same, it remains same. So, whatever arrangement here, the same we can see the arrangement in the undeformed and deformed regions. So, since the atomic movement is through the multiple one or multiple interatomic distances, therefore, it does not disturb the arrangement of the atoms in the deformed and undeformed regions. This kind of slip causes a step at the end. Width of the step developed depends on the extent of the slip or the movement of the sliding of layers of the atom which is taking place. Twinning is the another mechanism. Twinning mechanism of plastic deformation by twinning mechanisms involve the movement of one layer of atom over the another layer of atom only by fraction of interatomic distances, and because of this we will see that the deformed zone shows the different arrangement and orientation of the atoms as compared to that of the undeformed zones. Okay. Now, if we compare the slip and twinning, the two atomic level deformation mechanism, then we can see there are three important factors based on which we can compare. The slip occurs when the movement of layer of atoms on the slip plane is by one or multiple interatomic distances. But in case of the twinning, the slip occurs by the movement of one layer of atom over the another layer of atom by a fraction of interatomic distances, not the one or multiple interatomic distances. That is one. And because of this, we will see that in case of the slip, deformed and undeformed zones look same, but in case of the twinning, the deformed and undeformed zones exhibit the different orientation and arrangement of the atom. The deformation of the metal under the low temperature conditions and high strain rate conditions mainly occur by the twinning, but at a high temperature and low strain rate conditions it will be occurring by the slip. So, that the conditions under which the two mechanisms become active are different, but in real conditions, in reality, the deformation of the metal usually occurs by both slip and twinning mechanisms. Like what happens when the metal is subjected to the plastic deformation? Initially, in annealed condition, metal may have few incomplete plane of the atoms, that is dislocation, and when the metal is subjected to the plastic deformation, the number of incomplete planes increase, and that in turn increases the dislocation density. So, an increase in its yield strength of the metal is directly proportional to the square root of the number of dislocations when the dislocations are developed by the plastic deformation. So, yield strength becomes equal to the sigma naught, the yield strength of the metal in annealed condition, and A is the constant or coefficient, and the rho is the dislocation density and square root of the rho. Okay. So, here A square root of the rho sigma naught is equal to sigma y. It is like this, where sigma y is the shear stress required to cause the plastic deformation with this dislocation density of rho. So, sigma naught is the shear stress required to cause the dislocation to cause the deformation with the zero dislocation density or the metal in annealed condition, and A is the constant. This is what shows, like when the metal is having the different kind of the crystal structures, then how the critically resolved shear stress, the stress required to trigger the deformation by slip and twinning, that becomes different. So, say in case of the single crystal, what happens when it is subjected to the deformation by slip. So, the critically resolved shear stress required to cause the deformation in say Ag, it is 0.37, for copper 0.47, for aluminum 0.78, and for Mg 0.44, and like say HCP BCC metals show significantly higher critically resolved stresses, and this difference we can say that is due to the difference in the number of slip systems that these metals will be having. So, now I will summarize this presentation. In this presentation, basically I have talked about the various metal strengthening mechanisms and various microstructural aspects, including the crystal structure effect on the ease of plastic deformation and plasticity. Thank you for your attention.